Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, there are many fans of Sandpiles here. A couple of them are away this week in conferences, David Wilson and Ander Holroyd, so I'm very glad the talk will be recorded. So we're happy that Klaus Schmidt is here to tell us about Sandpiles and the harmonic model.
Well, thanks, Yuval, for the invitation. It's a pleasure to be here again after quite a few years when I was here last. I just noticed that the running footer is Sandpiles and other models. That sounds a little more ambitious than what I'm actually going to talk about, because I will not say, well, I'll say practically nothing about anything but these two models. So what I want to talk about is, well, first of all, let me offend you by telling you a little bit about Sandpiles, although everybody here probably knows much more about them than I do. So take a non-empty finite set in Z squared. For this talk, it's actually not at all important to restrict attention to Z squared. Exactly the same thing works for ZD. Then a configuration is an assignment of a positive integer to every element of this finite set lambda. And this configuration is called stable if the height of the each coordinate, or the size of each coordinate, is less than or equal to 4. So as you know well, this has some sort of heuristic interpretation that if the height is too large, then the pile of sand sitting there collapses. It's unstable, and it falls over. So the height gets reduced by 4, and the neighboring sites each get increased by 1. Of course, the site may still be unstable after a toppling, but then you just repeat it until it has become stable. Then, of course, the neighboring sites may become unstable in the process, so they topple, and you go through this process in some order. Turns out that it doesn't matter in which order you go through. And you end up with a new configuration, which is stable, which is called the stabilization, and which does, as I just said, not depend on the order in which you do this, perform the topplings. Then, so if you have a configuration, you can convert it into a stable configuration. And in particular, you can take a stable configuration, if you like, add a grain of sand somewhere, then let it stabilize again and see what you get. So this is a Markov process. I'm not going to tell you exactly what the Markov process is, but the sites, the edges of the Markov process are, so the vertices are the stable configurations, and the edges are the sites in lambda to which you can add a grain of sand. That would be one way of interpreting this Markov process. Then, this is something I've already said, that the order in which you do things doesn't matter. It also doesn't matter in which order you add, or where you add grains of sand. So here's a little example. You have a configuration, you add a grain of sand here, it becomes unstable, it topples, so it loses 2 grains of sand to these 2 coordinates, which become unstable, then they topple, and so on. And in the end, you have a stable configuration in this region. And something I forgot to say is that if a site like this one at the edge of the configuration is unstable, then you lose grains of sand because they fall into empty space. So this is the reason why this process actually works. So the stable configurations under addition and subsequent stabilization form a semigroup. And the recurrent configurations can be characterized either, or the set of recurrent configurations can be characterized either as the unique maximal subgroup of the stable configurations or as the recurrent states of the Markov process. And you can describe the set of that's the really interesting thing, the set of recurrent configurations. So here is one description of the recurrent configurations. You have your finite set lambda. You choose any subset E of lambda and any site in this subset. You look at the number of neighbors of this site in the subset E. And you look at those configurations for which, for at least one of the n's, the height is greater than the number of neighbors of that site. So that is, so you look at for lambda, you look at the configurations which for lambda satisfy this condition for every subset of lambda, and this is the space R lambda. So for example, in R lambda, you can never have two ones next to each other, because each of these two ones, so these two ones, they give you a subset of two adjacent coordinates. Each of these two coordinates has one neighbor in this subset, but the height does not, if the height in these two coordinates, in these two locations is 1, then this condition is clearly violated. If you take two regions, one contained in the other, then if you look at the recurrent configurations on the larger region and project it onto the smaller region, then you get recurrent configurations in the smaller region. So there is consistency which allows you to, now let me postpone that just for a second. So you have a group operation on R lambda, and you have a group operation on R lambda prime, and you can ask whether these two group operations are compatible in view of this inclusion, and the answer turns out to be no. So as the size of the region increases, the group structure, which we are discussing here, is not compatible. So here's a picture which I think I've stolen from your survey article. So these are squares of various sizes. And this is a picture of the identity element in the group we've just been discussing. And you see that the picture is roughly, or at least kind of similar, irrespective of the size of the region. So this says that the identities have nothing to do with each other, because if you look at this big region here, then this smaller region would actually comfortably fit inside this green square here, but it's clear that the identity here looks quite different from the restriction of the identity to this larger square. So as you tend to the limit, as you let this finite region tend to infinity, tend to z squared, you get a well-defined subshift of this alphabet, 1, 2, 3, 4 to the z squared. But the question is what happens to the group structure in this limiting process. This is called the two-dimensional critical sandpile model. Critical means, in this case, just the model I've described. There are other models where you reduce the height by more than the number of neighbors. And then you also have the same effect as here, where you use the edge to get rid of surplus grains of sand, and the behavior there is much simpler and certainly quite different. So what happens to addition on R lambda as lambda tends to infinity? It's clear that something has to fail, because if you have a configuration consisting of all 4s and you drop a grain of sand on it, then it can never stabilize. And you see computer animations, you can download them, and you see waves spreading out and coming in, and the process of stabilization never stops. So one of the questions which are very natural and which are studied to some extent. To what extent is R infinity? How much does it inherit from the group structure given for finite regions? If you can make sense of this group structure, or at least semi-group structure, what is the interaction between addition and the shift action on this space, which is also a well-defined dynamical system? There's an interesting formula which was proved by Deepak Dar in 2006 that the topological entropy of the shift action on R infinity is given by this expression, which deserves a star because it occurs for several other models as well. So it's some non-obvious number. It's in fact, if you're number theoretically inclined, it's the value of an L function somewhere. But it's, if I remember correctly, it's a number between 1 and 2, but I'm not sure. So here's another model. Let's go back. You have to memorize this number by heart because in future it'll only be referred to by star. So here's another model. Again, you take z squared and you take t to the z squared. So it's the Cartesian product of R mod z indexed by z squared. And you look at all configurations in this space which have the property that 4 times each coordinate is equal to the sum of the 4 neighboring coordinates, but modulo 1, of course, because you're in T, you're on the circle, you're not in R. So this is a linear recurrence relation defined by this polynomial. So every configuration in this space satisfies that if you convolve it by this polynomial, then you have 0. So if you like, if you plug in for u1 the horizontal shift and for u2 the vertical shift, then if you apply this expression, you just get 0 to every configuration in X. Then in 1990, Doug Lind and Tom Ward and I proved that the entropy is star, and Dan Rudolph and I proved that it's Bernoulli, of course, with that entropy. And the Hahn measure is the unique shift-invariant measure of maximal entropy on this space. So the dynamics of these systems is pretty well understood. Of course, there are many questions which you can ask which have not been answered, but at least these rough descriptions of the system are available. And it's called the two-dimensional harmonic model because this is a harmonic function for it. The value at each coordinate is the average of the values at the 4 neighbors, but on T you can't take averages, so you have to do it in this form. Here's the third model. You take the dimers on z squared. You look at the even shift action on this space. So the dimers means all configurations consisting of exact pairings of pairs of adjacent sites. You look at the shift action, the even shift action, so you shift by even amounts in each coordinate, and it has a unique measure of maximal entropy. The entropy is again given by star, and yes, I think the proof that it's Bernoulli is confirmed. So you have these 3 models. Oh, there's a 4th one, which I'm not going to explain, but which Russ can explain, and many others in the audience probably. So there are 4 models, 4 two-dimensional models like this. They all have the same topological entropy. At least 3 of them have unique shift-invariant measures of maximal entropy, which are Bernoulli. And the question is whether there are any connections between these models. So there are some very partial connections. The spanning tree model and the dimer model are nicely isomorphic. for every finite set, there is a natural bijection between the restrictions of the spanning tree model and the Sandpile model. But again, you get changes in this correspondence as the finite region changes. And there's one nice connection. There exists a continuous group homomorphism from the space of all bounded integer sequences or two-parameter sequences on Z squared to the harmonic model, such that it's equivariant with respect to the shift action. So this is the shift action on the Sandpile model. This is the shift action on the harmonic model, and the map is equivariant in this sense. If you restrict the map from L infinity to the Sandpile model, it's surjective. It sends the Sandpile model onto X. It sends every shift-invariant measure of maximal entropy on R infinity on the Sandpile model to the normalized H measure on the harmonic model. And the conjecture is that the connection can be made a little closer. So this says here that when you restrict the map to the Sandpile model, it doesn't drop entropy. So whatever kernel means, of course, it doesn't mean that the map is one-to-one or almost one-to-one or finite-to-one or anything like that, but there is no loss in entropy under this map. So in some sense, the pre-images of individual points in X cannot be very large. And the conjecture is that you can improve this, but unfortunately, this is a conjecture, not proved. So there's a closed shift-invariant subset of X such that the entropy of the action induced on this quotient group is the same as before. If you look at the map, now there is a map from this, If you restrict this map to the Sandpile model, then it's equivariant with respect to the shift action on this quotient group. It's still surjective. It sends every shift-invariant measure of maximal entropy to H measure of this quotient group. But this is just a repeat of what I've just said before. But the map is one-to-one almost everywhere with respect to at least one of these measures of maximal entropy, and that would imply uniqueness of the measure of maximal entropy on the Sandpile model. And that fact is, well, that is still an open problem. So this is something we've been thinking about for some time. At the moment, the problem is resting, but we haven't made sufficient progress to give an answer either way. Now, what I want to explain to you is how one gets a map like this from the space of bounded integer configurations to the harmonic model, which then, when you reduce it to the Sandpile model, gives you something at least close to what you want. And the method of proof goes back to an idea of Verbitskiy. I'll explain it in a much, much simpler setting, namely for a single toral automorphism. This is a hyperbolic automorphism of the two torus. It's an old friend. The entropy is the golden mean. And you can look at its expanding and contracting subspaces. So here's the expanding subspace. Here's the contracting subspace. The matrix is symmetric, so these two are actually at right angles to each other. And you have intersections, because this is the two torus. So this point here is the same as this point. And the contracting subspace through this point will intersect the expanding subspace through this copy of the origin. And here is one of these intersections. There are many. This is a dense set of intersections because these lines wrap around. And this point is called a homoclinic point because under backward iteration, it'll remember that it lies on the expanding subspace. So under backward iteration, it'll contract to 0 exponentially fast. And under forward iteration, it'll contract to 0, again infinitely fast. So this is a point whose forward and backward orbit converges to 0 quite rapidly. This line here, well, it extends and wraps around, and in fact it comes back here. So here's another intersection of this expanding and this contracting subspace. So this is another homoclinic point. Now, if you have one of these homoclinic points, then you can define a map from the bounded integer sequences to t squared by doing this. So you take this point, you move it through the automorphism alpha, and you multiply it by the nth coordinate. This is an integer, so this is something you can do in this group. And you get, by doing this, a map from L infinity to the group, which has this form, which is clearly equivariant. That's why you have a minus n here. And Verbitskiy showed in a couple of papers in 92 to 94 that the restriction of this map to the two-sided beta shift coming from the large eigenvalue beta is surjective. You don't have to know what the beta shift is. It's just a golden mean shift. So it's the sequences of zeros and ones with no two ones next to each other. Then if you restrict this map to these sequences, it's surjective. And if you choose a good x, the map is almost one-to-one. So you have a Markov shift, a topological Markov chain, and an equivariant continuous surjective map to this hyperbolic toral automorphism, such that the two systems are practically identified under this map. Now, a good homoclinic point is a homoclinic point whose orbit generates the group of all homoclinic points. So I'll show you here a good one. This is a good one. There are other good ones, but I haven't actually worked out which other good ones are visible in this diagram. So such a homoclinic point is called fundamental, and this is essentially how the map from the Sandpile model to the harmonic model is constructed. So in order to do this, you have to find a homoclinic point in the harmonic model, and then you use this homoclinic point to define a map from L infinity z squared z to the Sandpile model. And what you need from the harmonic model. Yes, sorry, I can't remember what I said, but this is what I meant. So how do you get homoclinic points of the harmonic model? So you take the polynomial, which we looked at before. So this is a polynomial with integer coefficients. This is the integer group ring of z squared, and you define an element f in this integer group ring, which has these coordinates. So at the origin, it has the coordinate 4. At the 4 neighbors of the origin, it has coordinate -1, and it's 0 otherwise. Then this element in the group ring, in the integer group ring, is not invertible in little L1 of z squared. But it's invertible after a fashion. It's just that the inverse doesn't lie in little L1. The inverse is in fact a scalar multiple of the potential function of the elementary random walk in z squared. If you take 1 over f, so this is 1 over take 1/4 of that. Well, so let's take 1/4 f. If we can invert that, then we are still in good shape. So this is 1 at the origin and 1/4 at the neighbors. Minus, yes. Yes. So if you take 1 over 1/4 f, this is equal to 1 over 1 minus nu, where nu is the equidistributed probability measure at the 4 neighbors of the origin. So this is equal to some nu to the k greater than or equal to 0. And this is how you get the Green's function of this probability measure, which is distributed at the 4 neighbors of the origin. So you add the powers, the convolution powers of this probability measure, and that gives you the potential function or Green's function of the elementary random walk. And because of recurrence, mass piles up at the origin. So you add up the first n convolution powers, and the weight at the origin increases because of recurrence of this process. You have typically infinitely many visits to the origin in this random walk. So you have to rescale the whole thing all the time, and you end up with a function which, when you go to the limit, has the value 0 at the origin and drops off. Yes, you're right. You just subtract. You subtract constants, and you end up with a function which is 0 at the origin and slowly drops off at logarithmic speed to minus infinity as you move out to infinity. Now you take this function, so this is this w here, and you look at multipliers of this function. This is in the convolution algebra of functions, real valued functions on z squared. And you're trying to find polynomials which have the property that when you convolve this potential function with this polynomial, it becomes summable. And in fact, such things exist. You can explicitly describe this ideal. For example, if you take 1 minus 1 times one of the neighbors of this of the origin. Notation is not very convenient for talking about it without writing anything down. So you look at the binomial term, 1 minus one of the neighbors. And you raise that to the 3rd power, then that's an element of this ideal. And the ideal is generated by precisely the 3rd powers of these binomial terms. So you can calculate this explicitly. Then for every h, for everything which lies in this ideal, but which is not a multiple of f, we obtain a homoclinic point by taking h dot w. This is now an element in little l1, so the coordinates of this point decay, and you get something summable. This point is an element of little l1. You reduce the coordinates modulo 1, and then this is an element of the group X. So this is now a homoclinic point of the group in the group X in this harmonic model, and one result is that every homoclinic point which has sufficient decay to be summable actually arises like this. Now this homoclinic point defines, this is now exactly like Vershik. Once you've got a homoclinic point, you can define the same map as before. So you take again the bounded integer arrays, and you define the map. So we have indexed the homoclinic point by this multiplier polynomial h. So that's the index which you see here. You take a bounded integer array. You take your homoclinic point xh, move it around, and multiply it by the corresponding coordinate of the bounded integer sequence. And the covering map is, well, this is already a more ambitious version of this. You take this map, then it turns out that when you restrict it to the Sandpile model, it's surjective and it's entropy preserving. Okay? Of course, it may not be the most economical map for doing that, because if you take an age which is unnecessarily large, so suppose you have an age which actually gets you into little L1, and you multiply this age by something else, then that new thing will still get you into L1, but it is unnecessarily large. In other words, this map psi age will a bigger kernel than before, and since we are interested in getting the map to be as close to one as possible, you are forced to try and be economical. So what you can do is you take the generators of this ideal, you can combine the homomorphisms coming from these various ages, combine them into a single map, and you get something which is entropy preserving and which is a candidate for being almost one-to-one, but we have not been able to prove that it is almost one-to-one. And this construction works for any dimension. In fact, things get a little easier with dimension greater than or equal to 3, because there the Green's function is bounded, but that's no major advantage in this game. For the, how am I doing for time? Maybe else. Yes, I think I will not abuse your patience unduly. So for the dissipative Sandpile model, where the toppling operators remove more than 4 grains of sand from each site, where you therefore have a reduction in the number of grains in the configuration, you get a nice result, the one we were hoping for the dissipative system.
The one you were hoping for the non-dissipative.
For the non-dissipative system, that the corresponding Sandpile model is in fact an almost one-to-one cover of the corresponding, well, what is this? Superharmonic algebraic model, where d times each coordinate is equal to the sum of the four neighbors. So there everything works fine. Also the various other aspects of the dynamics of both the dissipative Sandpile model and this algebraic model are much simpler, and the theory really works very well there, except it is the less interesting case. But let me still dwell for a moment on this and just discuss very briefly what more you can say about the connection between the dynamics on these harmonic, or maybe on this somewhat simpler version of the harmonic model, and the Sandpile model. So for example, what corresponds to dropping a grain of sand onto a Sandpile configuration? Well, for this group, it just means that you pick your favorite homoclinic point, which you used to get the covering map, and you add that homoclinic point to the group X. That's the exact analog. If you add something to the Sandpile model, you get the image of this under the map psi will be precisely the sum, the addition of this homoclinic point. So you see that the addition of a grain of sand corresponds to something extremely simple for this compact abelian group. You just add, it's just translation on this group. So if you choose a clever element, then you can say the dynamics is very simple. You get unique invariant measures for this. You get all sorts of nice things you can say about this. So let's go back for a moment to the critical sandpile model and see how much of that survives there. So you've got the critical sandpile model, and on the critical sandpile model, addition is not well defined. But it's clear that for some configurations, addition is well defined. So for example, if you take something very simple, like a configuration which nowhere exceeds 3, and you add grains of sand in various places, then the resulting element will still be an allowed configuration. Now, if you look at the image of this under the map Xi H, which you saw earlier, it's precisely group operation. Once again, you add various copies of your homoclinic point or various translates of your homoclinic point to the group. Similarly, if you take two configurations and you add them, well, in general, you can't do it in the Sandpile model, but if you can do it, then it corresponds to addition downstairs. Now, downstairs, you always have addition. So if you go upstairs and you take configurations and add them, then the pre-image of the sum downstairs will be, in a sense, and modulo the kernel of this map, the sum of the configurations upstairs. Well, you can play with that, but if for this to really make sense and to really give you information, you should know more about the injectiveness or lack thereof of this map from the bounded integer configurations to the harmonic model. So this is another nice feature of the dissipative Sandpile model. It actually has homoclinic points. There is a single homoclinic point which generates all of them. You don't need any multiplier ideals. And you can do exactly what Verbitskiy did for the two torus. Now let me waste a few more minutes by going a little further into the background of this. So criticality for the Sandpile model corresponds to non-expansiveness of the harmonic model. So the harmonic model, if you think about the definition of the harmonic model, assume that D is equal to 4. So if you assume that 4 times this coordinate is equal to the sum of the 4 neighbors, then you will see that this model has uncountably many fixed points. Each constant configuration will satisfy this condition. Therefore, this harmonic model cannot be expansive. If you have an expansive action, it has to have a finite number of fixed points. Otherwise, you run into trouble. Expansiveness means that you can not have 2 points in the space, in this case in the group X, whose orbits remain close together at all times. Now, if you have fixed points, well, nothing changes in their orbit. So if they're close, they stay close. Or if they ever get close, then they must have been close at the beginning. So the group X for the harmonic model is non-expansive, whereas for this model here, it turns out to be expansive. This requires proof, but it's not all that hard. And one of the really interesting problems is when you have homoclinic points for non-expansive models like this. I'll give you one example and then I'll stop. So there may not be an immediate natural candidate for a homoclinic point. You may have to do something to it, like what we saw earlier. You may have to multiply something. So you write down something which you think it would be nice to be a homoclinic point. It turns out not to be one. Then you multiply by something and you improve it. So for example, 4 minus x minus y minus x inverse minus y inverse, that's our old friend we've been talking about. Look at this polynomial in 2 variables, and you look at the variety of this polynomial. So you look at the set of zeros, C, in the complex numbers, such that f of c is equal to 0. So this is the complex variety of the polynomial f. Now, here we are using inverses, so we better be a little careful and we avoid 0. So we shouldn't take 0 here, but something like this. Now, in there, you've got the unitary part. So this is Vc of f intersected with s squared. Don't worry, I'm not going to go much further in doing this kind of stuff. So these are the complex numbers of absolute value.
Anywhere below that would become invisible.
Okay, I'll stop now. In fact, I think this is the last line I'm going to write. So you look at the points in this variety for which all the coordinates are of absolute value 1. Then the expansiveness is equivalent to the hypothesis that this intersection is empty. This is analogous to the statement that the toral automorphism is expansive if it has no eigenvalues of absolute value 1. In this case, there is a point which lies in this intersection. It's where x and y is equal to 1. Now the question whether there exist homoclinic points or whether you can produce homoclinic points by a method like this depends on the size of this set. In fact, it depends on the dimension of this set in s squared. If the codimension of this set, this is now for 2 possibly replaced by d, if the codimension is greater than or equal to 2, then you can do exactly the same thing, and you can happily define homoclinic points and covering maps of discrete models and do all this stuff for any kind of exotic model you might be interested in. But if the codimension is 1, then nothing works. And I'll stop with something on this line, which you can still see. So we had this polynomial. This was the harmonic model, which corresponds to the critical Sandpile model. If you do this, that's the dissipative Sandpile model, which is well behaved. And there, this intersection is empty because you can't get to 5 with pairs of numbers of absolute value 1. But if you take this here, then nothing's known, because this intersection here is a curve. It's something like a slightly irregular, well, not irregular, but dented circle. And there are no summable homoclinic points. So nothing I've been talking about works even remotely in this case. I should also say that once you have homoclinic points, you can do a lot more than this. You can, for example, prove very strong specification properties. So you can prove that if you look at configurations in some part of the space, so this is true for Sandpiles, for example, if you look at configurations on regions of the space, and then you look at another arbitrarily large configuration in some other region, if these 2 regions are separated by some specified amount, you can, within a small error, approximate anything you can see here and anything you can see here by a single point. And this kind of specification works if this set has codimension greater than or equal to 2, but it doesn't work for this example now. And we don't know whether this system still has these properties. Of course, no sane physicist would do Sandpiles with this property, where you keep getting, what happens here? Yes, you keep getting more stuff all the time, yes. Which is physically not very realistic, but you can still play with it. I think that's it. Thanks very much.
So when you're covering up the Sandpile over the harmonic model, what's the inverse of 0?
Yes, very good question. So basically what happens is, so if you take two configurations in the, so we have to go back a little. Take any configuration in L infinity z squared z, some bounded integer array. Suppose you have two configurations which differ in only a finite region, then you can interpret this difference as a Laurent polynomial. You have finitely many coordinates. Each of these coordinates can be identified with a monomial, where the first variable, if the coordinates are kl, then it's x to the k, y to the l. So if you take two configurations which differ in a finite region, then the difference is a Laurent polynomial. It may be some negative powers. And you can ask whether this Laurent polynomial is divisible by the polynomial f, which we keep talking about. So it's the one with 4 here. And the map which we are constructing identifies points which differ by a multiple of this polynomial. The difficulty is that points also get identified if there are infinite multiples of these polynomials. So if there are this polynomial times an infinite, if the difference is this polynomial times an infinite configuration. So for example, all threes is such a thing, I think. Anyway, you can, I withdraw that remark. But you can easily write down, so here's one way of getting something like this. So here is, am I too low? Is this too low? So take this configuration and add to it a shifted version of this configuration. So now we have -3, -3, 1, 1, 1, and so on. So you can build a strip consisting of -3s, 1s, and it continues. So this would be, and the rest is zeros. So this would be an infinite configuration, which is a multiple of f. So anything like this will get killed under the map psi x. Now, if you can have two legal Sandpile configurations which differ by something like this, and they will get identified. So
I guess I forgot a key part of my question, which is looking at the recurrent configurations that map to 0.
Yes, but you can have two recurrent configurations which differ by this, because you can have so this would allow you to oh, I see, now this. Okay, so we have to do one more level here. So this is also a multiple of f, but you can't see the bottom now. So it's two horizontal rows of 2s and 1s. So you can have two legal Sandpile configurations which differ by this expression. Therefore, they will get identified under the map. You look doubtful?
Well, I just don't see the answer to my question yet.
So you want to know?
I just want one first it would be one thing, one thing in the pre-image, and then I was really asking about what the entire pre-image was, but you just give me one thing in the pre-image.
I give you one thing in the pre-image, but I'm saying that all possible multiples of infinite multiples of f will get killed by the map psi. Now, some of these, so this is, of course, a huge set. And then you have to decide whether there are points, or sufficiently many points in the Sandpile model, to which you can add none of these pre-images without getting something disallowed. That's...
Reiterate that question. You want a particular, a critical configuration that maps itself to zero, not two with difference maps. So critical configuration,
yes.
Just numbers.
Add all threes to this.
You can't, then you have two ones next to each other.
No. If you add all threes to this, then you... Oh, I see now. All threes. Okay. Okay. If you take the point -2 everywhere, rather boring point, I must admit, you could add all fours to it. And then you get twos everywhere. And that is an allowed configuration. And you can do more complicated things. It's just that. So I don't think it's obvious how to get an explicit description of these things. But you can. It's not hard to write down specific examples, although I stumbled when I tried to do it.
Any other comments or questions? I think maybe we'll do that in private. So let's thank Klaus again.